In this paper, we introduced generalizing from references using a multitask reference and goal-driven RL framework. We showcase how to combine motion imitation and goal-driven reinforcement learning to obtain natural, robust, and generalizable behaviors for humanoids. Motion imitation method produces natural and coordinated motion, but it is brittle outside the demonstration distribution and tightly coupled to reference timing. On the other hand, pure task-driven reinforcement learning produces adaptive behaviors, but often results in unnatural or aggressive motion and requires heavy reward shaping. Our key idea is to treat reference motion as a training prior. We use references to shape motor skills and learn to adapt these skills toward new goals, ultimately executing without explicit reference tracking or phase input. Our framework trains a single policy jointly on two tasks. First, a reference-guided imitation task, which uses dense motion tracking rewards. Second, a goal-conditioned generalization task, which uses sparse task rewards and goals that are independent of the reference trajectory. We demonstrate this on box-based parkour tasks, including walk-jump, walk-climb, and climb-down behaviors. The objective is to adapt and compose these skills under new conditions. The policy receives proprioceptive input and a goal location provided by the mocap system. The critic additionally observes privileged information and a binary task indicator, since we have two tasks with different reward functions. Importantly, we do not provide target pose or phase variables. Instead, the combination of the current state and the goal implicitly defines the phase. To make this possible, a carefully designed curriculum is critical. We use two curriculum strategies and maintain a similarity metric that measures how closely the policy matches the reference motion. First, a wrench assist curriculum. We apply a large external stabilizing force early in training and gradually remove it as the policy becomes more stable. Second, a task mixing curriculum. We mix motion imitation environments, initialized from reference states, with generalization environments initialized from more randomized states. As training progresses, we gradually increase the proportion of generalization tasks. This transition allows the policy to first acquire stable motor skills and then generalize them. For the imitation task, we use reference state initialization, early termination based on deviation, and dense tracking rewards. For the generalization task, we use more randomized initializations and sparse goal-reaching rewards. Each behavior is trained from a single reference motion, with mirrored augmentation. We now evaluate how well the learned policies generalize to unseen initial conditions. We first show the walk-climb behavior. The first video shows the reference motion, and we also use its mirrored version for augmentation. Our method enables generalization across different starting positions. During testing, the pink box indicates the nominal position. In the top right video, the robot starts from the nominal position and climbs using the right leg first. In the bottom left video, the robot starts very close to the box and climbs directly using the left leg. In the last video, the robot starts farther away, walks naturally, and climbs using the left leg first. Next, we show the walk-jump behavior. The first video shows the reference motion. In the top right example, the robot starts from the nominal position, walks and then jumps up. In the bottom left example, the robot is very close to the box and jumps directly without walking. In the last video, the robot starts farther away and walks before jumping. We also show the climb-down behavior. The first video shows the reference motion. In the nominal and backward off-nominal examples, the robot behaves similarly. In the forward off-nominal case, the robot first moves slightly backward, sometimes overshooting, and then adjusts forward before descending. This illustrates adaptive behavior under unseen conditions. Next, we evaluate skill composition. We first demonstrate skill composition in the real world. Using a rule-based state machine, the robot successfully performs sequences such as jumping onto a box, climbing down, walking and climbing. This shows that the learned skills can be reused and composed. We also evaluate sim-to-sim transfer in MuJoCo. We test more challenging environment designs, as shown in the video, and observe interesting behaviors. For example, in the first video, the robot adapts its stepping pattern and uses different leg coordination to climb onto a higher platform. We compare our approach to two alternative training paradigms, tabula rasa reinforcement learning and pure motion imitation. In the jump-up example, pure motion imitation augmented with mocap information tends to move backward to better match the reference timing before jumping. Tabula rasa RL produces unnatural jumping behavior. In contrast, our method walks and jumps in a natural and adaptive manner. In the climb-up example, pure imitation again moves backward to align with the reference and then walks forward, even when already close to the edge. Tabula rasa RL fails to produce a coordinated climbing motion. Our method successfully walks and climbs in a natural way. We now examine which components are essential for training. In the ablation study, removing the generalization task prevents the policy from handling conditions far from nominal. Removing imitation results in less natural motion. Removing the task curriculum, by introducing full randomness from the beginning, causes instability and frequent falls. We also analyze task mixing. If we eventually train only on the generalization task, due to the sparse reward design, the policy forgets natural motion and behaves similarly to pure RL. Finally, without wrench assist, when initial conditions are randomized, the policy tends to learn unstable or unnatural behaviors. So far, we have focused on learning individual behaviors from reference motions. However, the proposed framework is not limited to this setting. To show the extensibility of our method, we further train a single policy conditioned on a one-hot skill embedding and elevation map observations. In simulation, the policy is able to execute multiple behaviors with perceptual inputs within a unified framework. Thank you for your attention.